Calculus.
No, please, no.
Capacitors.
No, anything but that.
Hey, person two, it's okay. It's okay. Give me 10 minutes, and I can show you how to use calculus to better understand capacitors. All right, let's go to the glass board. Hey, so we're going to analyze this circuit and figure out equations for the voltage across the devices as well as the current through the devices. But before we do that, let's take a step back and just get an intuitive sense for what's going on in the circuit. And we're going to look at a few different points in time or periods of time. One is the instant before the switch closes, and we're going to call that t equals 0 minus. One, the instant immediately after the switch closes. We'll call that t equals 0 plus. We'll also look at what's happening between the time that the switch closes and the time when the capacitor is fully charged. So we'll just call this, well, something's going to happen over time. Not over time, but over time. And then finally, as t reaches the end, approaches infinity, we'll see what infinity means. And what we're going to do is look at what is the voltage across the capacitor, what is the voltage across the resistor, and what is the current through the capacitor, which is equal to the current through the resistor. So before that switch closes, it's pretty simple to see what's going on. There's no current, there's no voltages across the devices. Everything here is going to be 0. Now the instant the switch closes, we make a complete circuit. We're starting with no charge on the capacitor, so the voltage on the capacitor at that instant is going to be 0. In order for Kirchhoff's voltage law to be true, the voltage across the resistor has to equal the voltage from the source. And if we have voltage across the resistor, the current through the resistor will be whatever that voltage is divided by that resistor. Then as time progresses, current's going to flow into the capacitor and charge is going to build up. As charge builds up, so does voltage, so voltage is going to start increasing. And again, to keep Kirchhoff's voltage law true, VR has to go down now. If the voltage across the resistor is going down, then the current through the resistor is also going down. After a period of time, that capacitor is going to get fully charged, and it's charging up to the voltage Vs. If the voltage across the capacitor is at Vs, the voltage across the resistor has to be 0, and the current in the circuit is now 0. The capacitor is full. You can't push any more charge onto the capacitor, and therefore you get the voltage Vs on Vc, nothing on VR, and no current flowing in the circuit. So now let's get more specific and see exactly what's happening as that capacitor is charging. And we're going to derive the equations for the voltage across the capacitor, the voltage across the resistor, and the current through those devices. And where we're going to start is with the definition of current. So that current, IR, which is equal to IC, is equal to the rate of change of charge over time. We're also going to use the definition for capacitor, and the voltage across the capacitor will be equal to the charge on the capacitor divided by its capacitance. And I've given the capacitance here as C, the resistance of the resistor is R, and you can see the voltages across the devices as well as the current through the devices. Now we have to look at Kirchhoff's voltage law. The voltage from the source has to be equal to the voltage across the resistor plus the voltage across the capacitor. Well, voltage across resistor is equal to current times resistance. And we could put in IR here, IR times R, but we also have already said what current is dq dt. So if I take that dq dt, or rate of change of charge over time, times the resistance plus Vc, I've just rewritten the equation in a different form. But now let's also replace this Vc with this definition for charge. It's Q over C. And now I've got a differential equation in terms of the charge. And there's different ways I could write the equation. But what I'm going to do is start with by isolating that dq dt over on one side of the equation. So dq dt is equal to Vs minus Q over C, all divided by R. Okay, again, I have a differential equation in terms of Q here, and I need to figure out an equation for Q in terms of time. And to do that, I'm going to need to use some calculus. And the first step I'm going to do is I'm going to split this dq and dt, and I'm going to put dq with all the q terms on one side of the equation and the dt with the other terms on the other side of the equation. So I end up with dq over vs minus q over c. So I took that expression and put it over that side of the equation, is equal to dt over r. So I took this dt and I moved it over to this side of the expression. I'm just going to do a little bit of rearranging of things here. I've got a c on the bottom of this term, and I actually am going to distribute it through this term and this term. So basically what I'm doing is multiplying by both sides of the equation by 1 over c, and I end up with CVS minus q equals dt over rc. Okay, remember I'm trying to solve an equation for q as a function of time. So what I'm going to do is I'm going to integrate both sides of this equation. And for this, remember, I'm starting with no charge on the capacitor, so I'm going to integrate from 0 up to some charge q. And let's say q is when it's fully charged, or it just could be any point. And over here, I'm integrating with respect to time, so I'm integrating from time 0 up to some arbitrary time t. So when I integrate this side of the equation, what I get is negative log CVS minus q, and I'm integrating from 0 up to q, and that's equal to t over rc, and I'm integrating from 0 up to t. Now I plug in q in this, and I subtract it when I plug in 0 to this, and same thing over here. I plug in the t to this part of the expression and subtract when I plug in 0 to this part of the expression. Actually, before I do that, let's move this negative sign over to this side of the expression, and what I'm going to get here is log, and over here I've got log of something minus log of something, so I can put that all together in one log function, or one log expression, CVS minus q over CVS, and that equals negative t over RC. Now, if I take the inverse log of both sides of this equation, e to the log of something is just going to be that something, and over here I'll get e to the negative t over RC. So I get CVS minus q over CVS is equal to e to the negative t over RC. Now remember, I'm trying to find q as a function of time, so I'm going to rearrange this equation and solve for q. And really, overall, I don't care about q as a function of time. I really care about the voltage across the capacitor as a function of time. Well, we can go back to this definition here for capacitance. So I know that Vc of t, or voltage across the capacitor as a function of time, is equal to the charge as a function of time divided by capacitance. So I can then take this expression here, CVS minus CVS e to the minus t over RC. So there's my q. And if I divide that whole thing by the capacitance, then I get Vc of t. Well, these capacitance terms all cancel out, and I get the expression voltage across the capacitor as a function of time equals Vs minus Vs e to the negative t over Rc. So I've got the equation for voltage across the capacitor. The other thing I want to know is the voltage across the resistor. Well, if I go back to Kirchhoff's voltage law here, I can see that VR will be Vs minus Vc. Well, with just a little bit of algebra, I've got Vs minus Vs, and then this will be plus Vs e to the negative t over Rc. And so those Vs's cancel out, and I get VR is equal to that source voltage times e to the negative t over Rc. And finally, the current. The current through the resistor is the same as the current through the capacitor, which will be the voltage across the resistor divided by R. So I would get Vs e to the negative t over Rc over R. And then that will just be the current at the initial closing of the switch. We have done a bit of work to derive these equations here. Now it is time to put them to use. And what I want you to do is for the value of R equals 1 kiloohm, C equals 2.2 microfarads, and Vs, or the source voltage, of 12 volts. I want you to figure out the values for VC, VR, and IC for a number of different points in time. So let's go with time 0 minus. So that's the instant right before the switch closes. At time equals 0 plus. So that's the instant after the switch closes. And then also I want you to try it at time 2.2 milliseconds, 4.4 milliseconds, 6.6 milliseconds, 8.8 milliseconds, and 11 milliseconds. So plug in these values for these particular times for the voltage across the capacitor, the voltage across the resistor, and the current through the resistor and capacitor. And then once you've figured out those values, then plot them and see what kind of shape the curves take. And see if it confirms our intuition about the way that the voltage and the currents change over time after that switch is closed. And you can check out the video that should be linked to from this card here, or you can check out the link in the description below for a video that will do exactly this, and you can confirm your answers. That video will also give you a little bit of insight into why I chose these particular values. Now before we go, I just want to let you know that there is an alternative way to deriving these equations here. And you can check out this video that will show you exactly how to do that. If you want to learn more about capacitors, including learning how to solve that problem you just saw, check out this playlist here. If you liked the video, click the thumbs up button. If you want to get more videos like this, be sure to subscribe. Thank you so much for spending your valuable time with me here. See you next time. Keep learning and have fun.